Hello, my dear friends. I am Shubham from LearnoHub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnohub.com. So then, let's start. So friends, as you all know, we are studying your ICSE chemistry chapter number 1, periodic properties and variations of properties physical and chemical. And so far we have studied till the metallic character. Okay, periodic properties we have studied until metallic character. Now in this video we are going to start with non-metallic character. Then we are going to see the trends in chemical reactivity and the trends in some physical properties. Okay, and then lastly we are going to solve some questions based on the concepts which we have learned so far. Okay, so without wasting much time, let's start and let's rock. Now, moving ahead, we are going to see now our third periodic property, non-metallic character. Okay, it would be just like similar to metallic character, but it is completely opposite to the metallic character. Okay, so chalo, let's start. Now, what is non-metallic character? Non-metal-like character. Okay, now what is actually non-metal-like character? Very simple. See, these character means tendency to gain electron. Okay, so if an element is having tendency to gain electron, we can say that that element is having non-metallic character or non-metal-like character. Now, why is this so? Because non-metals have tendency to gain electron, okay, to complete their octet, okay, and form anion. Okay, so let's see an example so that we would understand the non-metals. Okay, they are really having this tendency. See here, it is chlorine, non-metal. It is having 2,8,7 electronic configuration. Now you would figure out it is in badly need of just one electron so that it would attain octet. Okay, so it would complete the octet of its outermost shell. So what it would do is it would, like anything, crave for the electron, and what it would form? It would form an anion and it would complete its octet, okay, by gaining the electron. So see here, it's very evident, it's very clear that non-metals do have this tendency. And since what I said, if the element is having such tendency to gain electron, so we can say that that element is having non-metallic character. Okay, now more is the tendency to gain electron, then it's absolutely clear that the element is having more non-metal like character, okay, or more non-metallic character. So now let's see on which factors non-metallic character depends. Very simple, you know, first is atomic size, second would be nuclear charge. It won't change, okay, for all the periodic properties it would remain same. So now what we are going to see? We are going to see what happens to the periodic property or non-metallic character when atomic size increases. Okay, so first let's take this very cute loving atom. Okay, this is the nucleus of that atom, this is the outermost shell, okay, and this is the outermost electron. Now we all know this nucleus would be pulling this electron with some attractive force. Now what we would do is we would now increase the size of the atom. This would be the outermost shell, this would be the outermost electron. Now nucleus is also pulling this outermost electron with some attractive force. But now here we are going to see the attractive force which is being experienced on the which is being present or which is influencing, okay, actually on the outermost shell, okay, not just the electron but the nuclear attraction or nuclear influence on the outermost shell is the thing which we are now going to consider. So in this case, since the outermost shell is closer to the nucleus, so nucleus is having more influence over the outermost shell. So whenever an electron would come closer, okay, when that atom is trying to gain that electron, so since the nuclear influence is more here, okay, in this case, it would like pull that electron, okay, so it would be easy to gain an electron, okay, in this case, first case. Now just look upon the second case. Here the size has increased, so the outermost shell has moved farther from the nucleus. Now the influence of the nucleus or the attractive influence of the nucleus on the outermost shell would be definitely less than the previous case. Okay, so when an electron is coming here nearby, and when now this atom tries to gain this electron, okay, it would be considerably difficult for this atom to gain this electron as compared to this atom. Okay, the atom which is having smaller size. Why is this so? Because we know that here now the nuclear influence on the outermost shell is less as compared to the previous case. So it won't pull that electron that much strongly as it would pull this electron strongly. Okay, so if it won't pull the electron that much strongly, this means that the tendency to gain the electron in this case would be less than the previous case. Okay, suppose I am drawing two arrows is less than the previous case. Previous case would had tendency this much. Now, since the tendency to gain the electron is less, this means that non-metallic character of that atom, okay, of an element would also be less, right? Now, what happened? See, here the tendency is this much, so non-metallic character would also be this much. Now, you can clearly see what is happening. When we increased the size, okay, non-metallic character, what happened? The tendency decreased, right? Tendency decreased, so non-metallic character also decreased. That's it. Okay, now let's see what happens when the nuclear charge increases and what happens to whom? To the non-metallic character of the element. Okay, so let's take again a lovely atom whose nucleus is this much lovely. Okay, now this is the outermost shell, outermost electron, but what I told you, we are not going to see the nuclear attraction to the outermost electron. We are just going to see the nuclear attraction or nuclear influence on the outermost shell itself. That's it. So in this case, the nucleus is having, suppose, let's not see in the terms of arrows. Maybe arrows would be confusing to you. Let's take some numbers. Okay, numbers are very easy to understand. So if this nucleus is having some influence on the outermost shell. Okay, let's take it as 100. 100 is a very good number. Now what happens? Now we increase the nuclear charge. So what would happen is, after increasing the nuclear charge, now the influence on the outermost shell would definitely increase, right? It would be more. So it would be like more than this. So 120. So what happened? Now is it clear to you? See, when we increase the nuclear charge, so the attraction or the influence of the nucleus on the outermost shell also increased. Now, if the influence of the nucleus increases, what would happen? The tendency to gain the electron would increase, right? If it was like one arrow here, it would be now two arrows. Now, if the tendency to gain electron increases, this suggests us that the non-metallic character would also increase, right? Suppose if here the non-metallic character was just one arrow, but now since the tendency to gain the electron has increased, so non-metallic character would also that much only, that non-metallic character would also increase that much. So here, see, you can now clearly make out when we have increased the nuclear charge itself, non-metallic character also increased. Okay, now it's time to see the trends of the non-metallic character. So starting from down the group, when we move from top to the bottom in a group, what happens to the non-metallic character? Okay, let's try to find out. Same method, we are going to see the factors on which non-metallic character depends, what happens to those factors when we move down the group. Okay, so the two factors we know, just now we studied atomic size and nuclear charge, okay, on which non-metallic character depends. So what happens to non-metallic character when we move down the group? Just try to remember the picture of group 1 elements, okay, which we have studied. So what we have studied, that when we move down the group, the size increases. So make a picture in your brain that yes, oh, small, big, 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 big. Yes, that's it. So it would be clear, it would be easy for you to remember. So what happens when we move down the group? Size increases. Okay, atomic size increases. And what happens to the nuclear charge? Does it increase? Yes, absolutely. Because atomic number increases, therefore nuclear charge also increases. Okay. Now, what happens because of the increase in the atomic size to the non-metallic character? Just try to imagine. You should have a brilliant imagination power in order to get to the answers of this chapter. Okay. And it's very easy. Just try to imagine that, oh, I have increased the atomic size and just now we have studied. What would happen? Lesser would be the nucleus influence or nuclear influence on the outermost shell. So it would be less easy to gain the electrons, right? Less easy to gain electron means less is the tendency. Less is the tendency means less would be the non-metallic character, right? So non-metallic character would in short, decrease. Okay, because it is becoming less, so it would decrease. That's it. Now, when nuclear charge increases, what happens? The nuclear influence on the outermost shell will be more, so it would be easy to gain the electron. Easy to gain the electron means more is the tendency. More is the tendency means more would be the non-metallic character. So before the previous case, now it is more. Okay, in comparison to the previous case, now it would be the more. Okay, what is more? Non-metallic character would be more. So this means non-metallic character has increased, right? Now again the twist in the story, we know that the increase in the atomic size outweighs the increase in the nuclear charge, right? So the effect due to the increase in the atomic size would be more, right, than the increase in the nuclear charge. So I just draw two arrows. Now what would be the net effect? Net effect would be due to the increase in the atomic size, right? Because see here, we would cancel out. Then what remains is the effect due to the increase in the atomic size, which is decrease in the non-metallic character. So when we move down the group, non-metallic character decreases, which means that we would find the non-metals at the top of the group. Then slowly and gradually, when we move towards the bottom, we would find metals. Okay, so yes, decreases. And now let's say an example, it would be clear to you. So group 14 elements, here you can see carbon, silicon, germanium, tin, lead. Okay, so in this case, carbon we know all, it's non-metal. Then silicon and germanium, oh, they are the borderline elements. Do you remember boron, then silicon, germanium, then arsenic, antimony, right? So in this way we are moving the ladder, okay, or just stepping off from the stairs. In this way you have to remember, okay, boron, silicon, germanium, arsenic, antimony, in this way. So silicon, germanium are metalloids, we know that. And then after silicon, germanium, tin and lead are metals. Okay, so what we are seeing, the decreasing non-metallic character. Initially we would find non-metals, but later on when we move down the group, as we go down the group, at the end we would find metals. Okay, and in between we are finding some metalloids as well. So this is showing us the transition from non-metal to the metal character. Okay, now let's see what happens to the non-metallic character when we move across the period from left to right. Okay, so same, what happens, we just come to that conclusion at last, but in the process we just learn why it happens. So isn't it interesting? So we are going to follow the same process. Now let's see what happens to the non-metal character when we move across the period. So same logic we would apply. Okay, atomic size, nuclear charge, what happens to them when we move across the period? So when we move across the period, atomic size decreases. Same logic you would apply. You would just make an imagination, or you just remember the sizes of the atom, okay, in your brain. You know that lithium has the largest size, we have already seen, okay, 152 picometers as such it was the size, and then the fluorine size was very small, around 60 picometers. So the transition is like very much atom, then smaller, then smaller, then smaller, then smaller, then smaller, then smaller, like this. Okay, so what happens? Atomic size decreases, we know that. Okay, then what about the nuclear charge? Atomic number increases, so nuclear charge increases. Now what is the effect of decreasing atomic size on the non-metallic character? See, the atom size would be reduced, like decreasing, so the outermost shell would come closer, then the nuclear pull on the outermost shell would increase. Nuclear pull is increasing, so it would be more and more easier to gain the electron. If it is more and more easier to gain the electron, more and more would be the tendency to gain the electron. And if more and more is the tendency to gain the electron, we know that more and more would be the non-metallic character. So yes, we have reached the conclusion. The non-metallic character would increase. Okay. Now, what would happen when the nuclear charge increases? Same thing. Okay. When nuclear charge increases, nuclear influence, okay, on the outermost shell would increase slowly and gradually. So it would be easy to gain the electron. More and more would be the tendency to gain the electron. Same story. And more is the tendency to gain electron, then more and more would be the non-metallic character. So non-metallic character also increases. So the net effect would be increase in the non-metallic character. Very simple. Now, just pay attention to the example. These are the second period elements. These are the third period elements. What we see? Okay, we already know that these are lithium, beryllium are metals. Sodium, magnesium, aluminum are metals. We have already studied in the periodic table. Okay. Then boron, silicon. These are metalloids. Sorry. And then after metalloid, I have already told you, whatever would be the case, they all are non-metals. That's it. So carbon, nitrogen, oxygen, fluorine, non-metals, phosphorus, sulfur, chlorine, non-metals. So what you can observe the trend here is, see, from metal to non-metal, which means non-metallic character is increasing. We are moving towards non-metal, more and more towards non-metal. Okay, here also same, from metals to metalloids and then to non-metals. So this means non-metallic character is increasing. Okay, now let's see what are actually the oxidizing agents, okay, and the correlation between non-metallic character and oxidizing agent. Okay, so what are oxidizing agents? Such elements which gain electron to complete their octet are oxidizing agents. Okay, now see, we know that which elements gain electron to complete the octet. Do you remember the example? Chlorine gaining the electron, completing its octet, and chlorine is a non-metal. So yes, we can say that non-metals are oxidizing agents. Okay, simply. And see, the element, if they are gaining the electron to complete their octet, then that element is an oxidizing agent. So more would be its tendency to gain the electron, more would be the strength of that oxidizing agent. Okay, so simply more is the tendency to gain the electron, stronger would be the oxidizing agent, or we can also say in the other terms that more is the strength or more is the oxidizing nature, okay, of that element. Now you already know more is the tendency to gain electron, which this also means more is the non-metallic character. Now see here, non-metallic character and oxidizing nature are depending on the same factor, right? So that's why we can say that when more is a non-metallic character, it also means that it would be more is a non-metallic character. It also means that the oxidizing nature would also be more, right? So when we move across the period from left to right, we know that non-metallic character increases. Okay, so oxidizing nature would also be increasing simply. And when we move from top to bottom, non-metallic character decreases, so oxidizing nature would also be decreasing. Okay, so what do we conclude from this thing? Okay, I'm simply trying to tell you a simple trick that the trend of non-metallic character and oxidizing nature are same. Okay, so if someone asks you simply tell me the trend of oxidizing nature, you just remember the trend of non-metallic character and you would give the answer. Okay, now let's see the trend of basic nature of oxides of elements. Okay, so basic nature of oxides of elements. So suppose this is an element, okay, this is the oxide of element. When it combines with oxygen, we call it as oxide, right? And the basic nature, we are talking about the basic nature of this oxide of element. Okay, now when we see the trend, okay, from moving from down the group, means moving down the group from top to bottom, so we are considering the basic nature of oxide of metal. Here our element is metal. Okay, so basic nature of oxide of metal. Now what happens to the basic nature of oxide of metal? Here we can understand this with the help of an example. See, I have taken the example of group 1 metals. So their oxides are found to be, okay, when we are moving down the group, their oxides are found to be more and more basic in nature. The Na2O2 is more basic than Li2O, KO2 is more basic than both of these, RbO2 is more basic than this. So what is happening actually? The basic nature, okay, of the oxides of the metals down the group, it's increasing. Very simple. Okay, and now when we are seeing the trend of basic nature of oxide of elements, okay, not metals here. So in this case, when we are taking the example of, see, third period element, these are the oxides of elements Na2O, MgO, Al2O3, SiO2, P2O5, SO3 and Cl2O7. So what is happening to their nature? Okay, Na2O is very strongly basic, MgO is somewhat less basic, but Al2O3, oh, it has both basic and acidic character. Okay, so now the basic character is again less, and then SiO2, it's feebly acidic, then P2O5, it's acidic, SO3 more acidic, and Cl2O7 is like more acidic than SO2. Okay, strongly acidic. So what is happening? You can clearly see the basic nature is decreasing from more basic to less basic, then again much less basic, and so on, and then the rest oxides are acidic itself. Okay, so what is our conclusion? When we are moving across the period from left to right, basic nature of element is decreasing. Okay, now let's see what chemical reactivity means. Okay, so we can say a particular element is reactive when it has tendency to either lose electrons, okay, or to gain electrons. Now, we know which elements lose electrons readily. Metals, right? So, in case of metals, we can say that more is the tendency to lose electron, okay? More is the tendency to lose electron, then more would be the reactivity, okay? And similarly, in case of non-metals, we can say that more is the tendency to gain electron, okay? More is the tendency to gain electron, more would be the reactivity of non-metal. Okay, now let's see the trends in the chemical reactivity. First, we are going to see across the period. Okay, we have just slightly changed the pattern for this case. Okay, now when we are moving from across the period from left to right, what is actually happening? Let's understand with the help of an example. Okay, so I'm taking an example of third period elements: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. Okay, that's it. Now, what is happening? See, we would now just try to understand the variation of chemical reactivity based on the non-metallic character and metallic character. Now, why is it so? Because we now just now we have studied that the chemical reactivity depends upon the tendency to lose electron or tendency to gain electron, right? And now we also know that if more is the tendency to lose electron, more is the metallic character. So we would just try to figure out where the metallic character is increasing or where the non-metallic character is increasing, so that we would understand actually is the tendency to lose electron increasing or decreasing, or is the tendency to lose electron tendency to gain electron increasing or decreasing. Okay, feeling like a bit messy. Okay, let's make it simple. See, we will see this example and you would totally understand what I'm trying to say to you. Okay, so now from moving from sodium to magnesium to aluminium, okay, we all know that these are metals. This is a metalloid, right? And these all are non-metals again. So what we would do, we would first figure out the metallic characters variation across the period. Okay, since these are metals here, okay, so we would just figure out what is happening to the metallic character. Now we all know metallic character decreases across the period. How I figured it out? Very quickly. Just I'm telling you the trick. Okay, you have to remember the logic as well, but you have to understand the concept as well. But just remember a trick to determine how the metallic character increases or decreases across a period. See, here there are metals, here there are non-metals. So if I'm moving from left to right, okay, since there are non-metals, okay, so the metallic character here is less, here it is more. From more to less means it is decreasing. Simple. So here metallic character is decreasing. Okay, when we move from sodium to magnesium to aluminium. Is it clear now? Okay. Now, what we can conclude from the decrease in the metallic character? The point which we actually want. We want to actually check what is happening to the tendency to lose electron or tendency to gain electron. Now, here there are metals, so we are considering metallic character. Now, metallic character is decreasing. This suggests us that the tendency to lose electron is decreasing. Okay. Now, if the tendency to lose electron is decreasing, we know reactivity will be decreasing simply, right? So, when we move from left to right, okay, initially reactivity is decreasing and now it reaches a least point at the metalloid silicon. But after that, oh, there is a twist in the game, there is a twist in the story. What is happening? See, here there are non-metals. Okay, now let's try to understand this with the help of non-metallic character. What is happening here? So we know that non-metallic character across the period it increases. Now same logic, you remember, you know, here there are metals, here there are non-metals, so non-metallic character here is more, here it is less. From less to more means it is increasing. Okay, so non-metallic character would increase as we move from phosphorus to sulfur to chlorine as well. Okay, now what does this suggest to us? If non-metallic character is increasing, this means that the tendency to gain electron is increasing. Okay, and if tendency to gain electron is increasing, this means the reactivity is increasing. Very simple. So what is happening? We have concluded, we have reached the conclusion. Initially, when we move across the period from left to right, reactivity starts decreasing. Okay, and then it starts to increase. That's it. Very simple. Now let's see the chemical reactivities trend when we move down the group from top to bottom. But first, we are seeing this thing in case of metals. Okay, so you all know metals are towards the left of the periodic table. So we are like, means actually more than 75% of the periodic table, okay, the elements in the periodic table are metals, right? But the most metallic elements are this, the group 1 and group 2. So now in this case, we are taking the example of group 1 and group 2. We are not studying in detail about group 3, from group 3 to group 12, okay? So in this case, what is happening? See, we will just figure out it in the same way as we figured out in case of across the period. So here, from lithium to sodium to potassium, then rubidium, cesium, we know that metallic character is increasing as we go down the group, okay? Now, see how we could figure out this. Now we have to rely on the logic, okay? No more chance, because see, now we know that when we move across the period, okay, all these are metals, so we cannot have the trick. But it's very simple. See, the atomic size is increasing quickly. This thing should come in your mind. So if the atomic size is increasing, nuclear charge is also increasing. But we studied that increase in the atomic size is more than the increase in the nuclear charge. So net effect would be because of the increase in the atomic size. Now what is the effect of increase in the atomic size on metallic character? Just try to imagine. When the atomic size is increasing, what would happen? The electron would be moving further and farther away from the nucleus. So it would be easier and easier for the atom to lose the electron. And if it is easier and easier to lose the electron, that means the tendency to lose the electron is increasing and increasing. Now tendency is increasing and increasing to lose the electron, which means metallic character would also be increasing and increasing. So yes, we reach the metallic character, we reach this point, which means we reach this point that we have already concluded that metallic character is increasing, okay? So how metallic character is increasing? We reach that point, okay? Now, what does this suggest to us? We already have gone through that point. The tendency to lose electron is increasing and increasing. That was our point, okay? So tendency is increasing to lose the electron. This means that reactivity would be increasing when we move from top to bottom in a group in case of metal. Now let's see what is happening to the chemical reactivity when we move from down the group, means when we move down the group from top to bottom in case of non-metals, okay? So non-metals, we know they are towards the right of the periodic table, okay? Now I am taking an example of this group 17 elements, okay? What is happening with them? Let's try to figure it out, okay, with the help of non-metallic character now, because we are seeing the case of non-metals. So when we move down the group, we have already studied non-metallic character is decreasing, okay? Now how I figured it out very quickly, the same logic we would use. We know that atomic size is increasing, nuclear charge is also increasing when we move down the group, but increase in the atomic size is more than the increase in the nuclear charge. So the net effect would be because of the increase in the atomic size, right? Now, if the net effect is because of the increase in the atomic size, what is the effect of the increase in the atomic size then? We have to just remember that thing. So when the atomic size is increasing, just imagine the electron is moving farther and farther from the nucleus, which means that the outermost shell is also moving farther and farther from the nucleus. So the nuclear influence on the outermost shell would be lesser and lesser. So when the electron would come near the outermost shell, it would be difficult for the atom to gain that electron. So the tendency would be less and less, okay? It would decrease, and it would decrease and decrease more. Which tendency? Tendency to gain the electron, okay? Now if the tendency to gain the electron is decreasing, this means non-metallic character is decreasing. And now yes, with this we figured out the tendency to gain the electron is decreasing, right? This means that reactivity is decreasing. Okay students, so now let's try to find out the most reactive metal in the periodic table, okay, and the most reactive non-metal, okay. So answer is in front of you, but we will find out it, okay, right now. So we know that just now we have studied the trends in the reactivity, okay, across the period, down the group. So it is clear, we now clearly know that the reactivity, okay, in case of a period, okay, it's more at the extremes, okay, because now just now we studied that reactivity goes on decreasing and then again it goes on increasing. So the reactivity in a period is highest at extremes, okay. So now if I consider this period, the reactivity is highest in case of lithium, okay, and fluorine, okay. Similarly in the second period, sodium and chlorine, third period, potassium and bromine, and so on, okay. So now till astatine, the iodine and astatine are also most reactive in that particular periods. Rubidium, cesium are also most reactive in the particular periods. Okay, I have just skipped this francium and tennessine because we all know that this francium is radioactive. Okay, so its radioactivity creates problem in its study, and as well as this tennessine also, it's now a recently discovered element. Okay, so we haven't studied that element in much detail. Okay, so forget about the last period, just focus till the 6th period. Okay, the reasons I have told you. Now what our actual point is to find out the most reactive metal and most reactive non-metal, right? So in this context, what we found out right now, we found out the most reactive elements. Okay, so these are the most reactive elements, group 1 and group 17. Now among this, we have to find out most reactive metals and most reactive non-metal. Okay, most reactive metal. Now we know that this group 1 are metals. So yes, we found that these all are reactive, most reactive metals. But now which one among this is most reactive? Okay, this is the question. And once we find out which one among this is most reactive, we got our most reactive metal in the periodic table. Now see, among all these lithium, sodium, potassium, rubidium, cesium, now we would apply the concept of the chemical reactivity trend down the group. What we saw? In case of metals, when we moved down the group, reactivity was increasing. Okay, just now a few slides ago we saw that. So reactivity is increasing when we move down the group. Now this means that sodium is more reactive than lithium, potassium is more reactive than sodium and lithium, and so on. Okay, so this means cesium is most reactive, right? Cesium is more reactive than all these elements, and among the most reactive elements, cesium is most reactive. Yes, and this is our answer then. So yes, we got our answer. Cesium is the most reactive, okay, which is present at the bottom of the group 1. Now similarly, we are going to see the most reactive non-metal. So we have already the most reactive non-metals, okay, group of most reactive non-metals. Among this, when we move down the group, we are now applying the concept of what happens to the reactivity in case of non-metals when we move down the group. So what happens? Reactivity goes on decreasing. Okay. Now this means that astatine is the least reactive one and fluorine would be the most reactive one among all this, right? Among all this. And yes, since these all are the most reactive non-metals and among them fluorine is most reactive. So we got our answer, right? Fluorine, which is present at the top of the group 17. So now moving ahead to the last topic of this video. After that, we are going to solve some questions. So let's see the gradation in the physical properties. Now, which two physical properties we are going to see? Melting point and boiling point. Okay, these are the two, and one more is density. So first, we are going to see the melting point and boiling points gradation simultaneously. Okay, so what is happening to the melting point and the boiling point when we are moving down the group from top to bottom in case of metals? Okay, so here is the data in front of you. Lithium, sodium, potassium, we are moving down the group. What is happening to the melting point? 180, 94, 63, it is decreasing. What is happening to the boiling point? 1347, 883, 774, it is also decreasing. So yes, we understood that melting point and boiling point in case of metals, when we move down the group, it decreases, right? Now, here in case of non-metals, what is happening? Let's see. Melting point minus 219, minus 101, minus 7.2. So here we can see that we know the number line, right? From minus 219 to minus 101, then to minus 7.2, and then again moving to the plus 113. So what actually we are seeing is the melting point is increasing, right? From minus to plus. So this was the variation on melting point in case of non-metals, fluorine, chlorine, bromine, iodine. Now let's see the boiling points variation. Okay, it is increasing here. Now boiling point minus 187, minus 34, again increasing, plus 58, oh, increased, and then plus 83, plus 183, again increased. So boiling point is also increasing. So in case of non-metals, boiling point and melting point increases. Okay, now let's see the variation in melting point and boiling point when we move across the period. Okay, now what is happening? See, when we are moving from left to right, okay, across the period, here in this way, and I have taken the example of third period elements. Okay, we only have the data of melting point, but the boiling point is also showing the same variation as that of melting point. Okay, now let's see what melting point's variation is. from 98 to 650, from sodium to magnesium, then 660, again it's increasing, then 1410, again it's increasing. But yes, this is group 14, right? The group 1, group 2, group 13, group 14. Now here in this case, after group 14, it is decreasing, see 44.2, and then it's slightly increasing, but the net is decreased. You can observe here 1410 to 115.2. So net is decreased. So what we have observed, when we move across the period from left to right, melting point, and yes, we don't have the data of boiling point, but yes, boiling point also follows the same trend. What trend they follow? They increase till group 14, okay, and then they start to decrease. Okay, now let's see the gradation in density or variation in density when we move down the group and across the period. Now, firstly, down the group, what is happening to the density? Let's see with the help of an example. See, lithium, sodium, potassium, rubidium, cesium. Density is 0.5, 0.9, 0.86. Okay, it's increasing here, slight decrease. But then see, 1.5, 1.8, it is again increasing. So we can say the net is increase, right? Just a slight deviation. But if we ignore this slight deviation, we can find out that the density is increasing. Okay, so what is happening? Density increases when we move from top to bottom in a group. Okay, now moving to the across the period trend, when we move from left to right, what is happening? We have taken an example of this third period elements. Okay, sodium, magnesium, aluminum, silicon, phosphorus, sulfur. Now the density is here in the case of sodium is 1, magnesium 1.7, it's increasing, then again 2.7, again increasing, but after that, see, it's decreasing, 2.3, then 1.8 and 2.1. So we are observing the increase till a maximum value, and then after that we are finding a slight decrease from 2.7 to 2.1. So what actually the trend is, it increases till the maximum value. See, in this case here it is the maximum value from 1 to 1.7 to 2.7, and then it is showing a slight decrease in the density when we move across the period from left to right. Now it's time to see some questions. So first one is, which is greater in size, Fe2 plus, Fe3 plus. Okay, now do you remember we have learned the concept of the cations of same element? Okay, so when the charge on the cation of same element, here it is Fe, okay, if the charge is more, okay, or the cation is having, which is having more charge, more positive charge, it is having smaller size. Okay, we have already learned this. You can go back to that section, you can again understand the concept, okay, if you feel you have missed it. Okay, now this means that here in this case the cation which is having more positive charge is Fe3 plus, so it would be having smaller size, so it would be having smaller size than the other cation Fe2 plus. Now just go back again to the question, what they are asking, which is greater in size. Okay, so don't be in a hurry that, oh, I got the answer, this is smaller in size, I would write there. They have asked which is greater in size, so this one is greater in size, right, among both this. So our answer is Fe2 plus. Okay, now moving ahead, arrange beryllium, lithium, carbon, boron, nitrogen, oxygen, fluorine in increasing metallic character. So actually you can make out, see, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. They have given us second period elements, in fact. Okay, now we all know in case of second period, in case of a period when we move from left to right, what happens? Okay, there are non-metals, here there are metals. So here metallic character is more, then metallic character is less. So what is happening to the metallic character? From more to less. Its transition is from more to less. This means that the metallic character is decreasing. Yes. So now we clearly know that when we move from lithium to fluorine, okay, metallic character is decreasing. Okay, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay, in this case, so the most metallic is lithium, least metallic is fluorine. Now what in which order we have to arrange? In increasing order of the metallic character. Okay, so first we would start with the least metallic character element. So least is fluorine, right, on that extreme. Then when we would see, when we are moving from left to right, metallic character is decreasing. So apply the ulta logic, okay, opposite logic. When we would move from right to left, metallic character would increase. So we have to just arrange the elements in that order. Okay, so metallic character is increasing, so oxygen is having more metallic character than fluorine. So oxygen, yes, more metallic character than fluorine. Nitrogen is having even more metallic character than oxygen. So nitrogen having more metallic character than oxygen. Then carbon, it is also having more metallic character than oxygen. Okay. Moving ahead, boron, it is having more metallic character than oxygen. Then beryllium, it is also having more metallic character than oxygen. Sorry, more metallic character than boron. Okay. And then lastly is lithium. Okay. So what I can do is I can write this again here so that you won't feel confused. Yes, lithium. So this is our answer. Okay, now this one, B, silicon, sodium, aluminium, magnesium, chlorine, phosphorus, sulfur. Okay, we have to arrange these elements in decreasing non-metallic character. So what we would do, we would first see what all these, we would just try to locate, or we would just see from which period these elements are belonging. Okay, very simple. See, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, these are third period elements. Okay, now we would figure out what happens to the non-metallic character when we move across the period. So when we move from left to right in a period, non-metallic character increases. Okay, I have already told you the trick. Here there are metals, here there are non-metals. So here in this side non-metallic character is more, here it is less. So from less to more means non-metallic character is increasing. Okay, now what they are asking to do is they are asking to arrange these elements in decreasing non-metallic character. Okay, so the last one should be having, the last element should be having least non-metallic character. Okay, so we know that the third period starts from sodium to chlorine. Okay, means argon, but here there is no argon. Okay, we have to just arrange till chlorine. Now non-metallic character is increasing from left to right, but see, we have to arrange in decreasing non-metallic character. So when it would decrease, when we would move from right to left, non-metallic character would decrease, right? Ulta. From left to right it is increasing, from right to left it is decreasing. So this means sodium has least non-metallic character, chlorine has most non-metallic character. Okay, so first which would come? Chlorine. Okay, among all these elements. So I would just arrange these elements here: sodium, then magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. So chlorine is having most non-metallic character, so it would come first. Then we are arranging the decreasing order. So which element is having less non-metallic character than chlorine? Just next to it, because here in this case when we are moving from left to right, non-metallic character is decreasing. So here it would be less. Okay, from when we would move from chlorine to sulfur, the non-metallic character would be less, right? So sulfur is having less non-metallic character than chlorine. Then again, if when we are moving from sulfur to phosphorus, non-metallic character is decreasing. So phosphorus, this means, is having less non-metallic character than sulfur. Then again when we are moving from phosphorus to silicon, right, non-metallic character is decreasing. So this means silicon is having less non-metallic character than phosphorus. Again it is decreasing. This means aluminium is having less non-metallic character than silicon, and again decreasing. This means magnesium is having less metallic character than aluminium. And yes, lastly sodium. So I would just write it here again so that you won't get confused. Silicon, aluminium, and then magnesium. And then lastly, the least non-metallic character element is sodium among all these things. Okay, so our right answer is this. Now moving on to the next question. Which one of the following has the largest atomic radius? Okay, very interesting question. See, the options are sodium, potassium, magnesium, aluminium. Now what we have to do first is we have to just locate all these elements. Where do they belong in the periodic table? Okay, so now see, I am also having a plain paper like you, so I would be locating the elements like you only. Okay, like your examination. So sodium belongs to the third period, right? After sodium, see, potassium belongs to the fourth period, just below sodium. Okay, then magnesium and aluminium. So magnesium just belongs next to the sodium, right, in the group number 2, third period. And then comes aluminium, group number 13. Okay, third period. Now see, among this is third period, this is fourth period. Now we clearly know that when we move down the group, what happens? Atomic size increases or atomic radius increases. When we move across the period, what happens? Atomic radius decreases. Okay, I have already told you the trick. Just try to sizes of the atoms. Okay, the comparative sizes. Now we know across the period the circles become smaller and smaller, the sizes become smaller and smaller. We have already learned the concept. Okay, and when we move down the group, the atomic size increases, circle become larger and larger. Okay, which means the size becomes more and more. So you can remember in this fashion. Okay, down the group size becomes more and more, atomic radius increases. Here down across the period size becomes less and less, so atomic radius decreases. Now what we have to find, among these elements which one has the largest atomic radius. Now see, sodium and potassium, let's compare them first. When we move down the group, we know atomic radius increases. This means potassium's atomic radius is more than the sodium, right? Now let's see potassium's comparison with magnesium and aluminium. Okay, but for that let's try to think logically. See, we know that across the period when we move, okay, from left to right, what happens to the atomic radius? It decreases. So this means that atomic radius of sodium is largest, okay, among all the elements, right? So among magnesium and aluminium and sodium has the largest atomic radius. So this means that, see, if sodium is having largest atomic radius, their magnesium and aluminium's atomic radius are even smaller than sodium. So let's try to visualize it. Okay, see, potassium's atomic size is more than sodium's atomic size, and just now we have figured out the magnesium and aluminium's atomic size are even smaller than sodium. See, even smaller than sodium. So now what you can infer, that potassium, okay, is having the largest atomic radius among all these four elements. Isn't it easy? Okay. Next, which one has the largest size? Bromine, iodine, iodide ion, okay, I minus ion, and chlorine. Okay, so now the same fashion. See, we will just try to figure out, we will just try to locate them. So see here, first bromine comes, first chlorine comes, then bromine, and then iodine. Okay, when we move down the group, and iodide ion. Now this iodide ion or I minus ion is formed when iodine gains electron. Okay, so let's see it later on. First let's try to compare their sizes. Okay, so when we move down the group, again the same thing, the picture of visual, you have to visualize that. See, down the group when we move, the sizes becomes larger and larger of the atom. Okay, so it's very clear that iodine is having the largest size among chlorine, bromine, and iodine. Okay, now let's compare the iodine size with I minus. Okay, let's see whether this one is having larger size or iodine is having larger size. Now you would have, now something would have been clicked in your mind. We have already studied the anion. Okay, the size of the anion is greater, right, than the parent atom. Okay, so you can go back to the video, go back in the video, and you can see, if you want to, the reason of this thing in detail. Okay, but now here we have already figured out that yes, size of the anion is greater than the parent atom. So this is the anion, right, and this is the parent atom. Now this anion size is greater than the parent atom. Okay, so iodine size is greater among chlorine, bromine, and iodine, and iodide ions or I minus ion size is more than iodine. Okay, so now it has been the same case, it has become the same case. So this means that I minus ion is having the largest size. Okay, this chlorine, this bromine, and chlorine are having even smaller sizes, okay, than iodine. So that's why, and we know that now this I minus ion size is more than the iodine, right? So this is having the largest size among all these elements. So friends, with this we have reached the end of this video, and I hope you all would have enjoyed learning with me and you would have understood all the concepts so far we have learned. But please do let me know whether you have understood all the concepts or not. And yes, we are going to meet in the next video with the remaining concepts of this chapter. And as you all know, LearnoHub matlab free hai par best hai. So see you in the next video. Stay tuned. Bye bye and have a great day.